Jullian Yapeter. He's a machine learning scientist at Signal One. In his bio reads, his focus is at the intersection of model development and ML infrastructure and ML ops. He's an engineer with a BASc in mechatronics engineering from the University of Waterloo and an MS in computer science from the University of Southern California. He was a research assistant at the CLVR labs at USC, working on large-scale offline RL under Prof. Joseph Lim. Jullian has industry experience working on AI computer vision systems at Disney, Imagineering, IBM, and a few different startups. Overall, he's passionate about improving people's lives through technology, and his talk will be AI for hospitals at scale. Jullian, take it away.
Awesome. Hello, can you all hear me okay? Good? Awesome. Thank you so much, and good morning. It's really an honor to be here among so many passionate and amazing ML researchers and practitioners. I'm Jullian Yapeter. I'm an ML scientist at Signal One, and today I'll be talking to you all about AI for hospitals at scale. So a little bit about Signal One. For the past 2 years, we've been on a mission to empower clinicians and care providers with timely, accurate information to enable better patient care and improve patient outcomes. And it's an exciting problem, the healthcare space with ML. And I wanted to start with a story as to why this is an important problem. So one day, a doctor was on her shift in the internal medicine unit at St. Michael's Hospital when she received an alert from her phone about a patient who was deteriorating. So she examined the patient, and at first glance, everything looked fine. But just to be safe, she ordered a blood test for the patient. When the results came back, it showed that the patient's liver enzymes were elevated. And this was cause for concern. And just as the patient was about to go into further imaging for her liver, the patient developed fever and abdominal pains. But what this showed was that the alert helped clinicians act earlier and ultimately saved the patient's life. And this is a true story. You can read about it in this Globe and Mail article right here. The alert was sent by an AI tool called ChartWatch, which was developed by our partners at St. Michael's Hospital. And this is great because it proves that in at least one hospital and one use case, that AI can be a powerful life-saving tool. The question is, can it scale? And that's the question that Signal One is tackling. And when I say scale, I mean 3 different things. 1, can it generalize to other hospitals, to many more hospitals? Can we reduce the time it takes to deploy ML models in hospitals because there's so much work involved to interface with the hospital to get this deployed? Can we reduce that time? Can we also streamline the deployment process? Because there's a lot of manual procedural work involved in doing this. Can we minimize the amount of manual work to take a model and replicate it and deploy it to other hospitals? So today I want you all to come with me on a journey to develop this end-to-end solution. And there's a lot to cover. So where do we start? As always, we start at the beginning with a blank canvas. And I think there's nothing really more exciting than a blank canvas because it represents all the possibilities, right? And I guess for us ML practitioners, that blank canvas looks kind of like this, like an empty PyTorch function. And you might get excited. You start to get excited to start putting paint to canvas and start implementing your model and designing your architecture. But the truth is, there's a lot to do before you ever pick up a paintbrush and a lot to do after you put it down. They say a problem well-defined is a problem half-solved. So let's start with that. Let's define our problem. What is the subject of our painting today? What is the ML problem? What do we want to predict? What are the inputs and outputs? So there's a huge variety of ML problems in the healthcare space, a huge variety. Signal One tackles a handful of them. But today, let's focus on one, and that's patient deterioration prediction. So that's very similar to the story I told you in the beginning. The goal here is to alert clinicians of patients who are at high risk of deteriorating. 48 hours before it happens. So simple enough, you can frame this as a logistic regression problem where you take as input data about the patient and you output a classification on whether the patient will deteriorate and whether or not to send an alert. And the probability distribution of this model represents the confidence that the model is in a patient that will deteriorate. Of course, there's still a lot more questions like what really is the data that we're inputting into the model? What does it mean for a patient to deteriorate? How far in advance do we want to predict? And what kind of predictive performance do we need, right? But that's all for later. At least for now, we've framed our problem. We've decided on the subject of the painting, and that's this flower right here. The next question is, what's our palette? What do we have at our disposal to create this model? What data do we have? So when Signal 1 works with a hospital, we connect to their electronic health record system, or EHR for short. The industry standard of storing and retrieving and writing this data is called FHIR, F-H-I-R. It stands for Fast Healthcare Interoperability Resource. What you need to know about FHIR is that it defines a whole bunch of types of medical data. It defines what they mean, but it also defines the structure of the data. And it standardizes everything in a nice way. And it also provides a REST API for retrieving and writing FHIR information. The other thing you need to know about FHIR is that it's modularized into these interconnected resources. And a resource is simply a concept characterized by a data structure object. So a patient is one object. An observation is one object. That's like a lab or vital. The medication is one object. Service request, procedure, those are all interconnected objects in this FHIR standard. So actually, a lot of our work is digging through this insanely rich treasure trove of information to figure out what's useful and what's not. And with this FHIR data, you can see a patient's journey through the hospital. You can see all the events that occur and all the data that's involved, including static data like the patient's age and sex. You can see what units they got admitted to, transferred between. You get to see what their vitals were at different points in time. You can see when lab tests were ordered for the patient and what the results were. And all of this, we call this an encounter, a whole patient journey in the hospital. And all of these events make up your palette. This is what you can work with to develop your model. The thing is, not any two hospitals are created equal. In terms of where certain pieces of data live within the FHIR structure, it can differ between hospitals. Different hospitals can measure different measurements in a different unit. For example, body temperature at one hospital could be Celsius, could be Fahrenheit at another. We even saw Kelvin in another hospital. And each hospital has their own idiosyncrasies, right? They have their own nuances and personality. Like some hospitals use a -1 flag to mean it wasn't measured. This thing wasn't measured. So the challenge about deploying at many hospitals is that all these deviations from the mean need to be reconciled. But we don't want to do it in a manual way because we know that manual work is not scalable. So how do we do it? We have a two-part pipeline for scalable data extraction and pre-processing. First, we select clinically grounded data. So this is data that we know are less likely to suffer from the domain gap problem, things that are more rooted in human biology, like someone's blood pressure. Regardless of where you are, human blood pressure follows a certain distribution as long as we measure it in the same unit of measurement. But something like the time at which a person gets transferred to the ICU, now that might be a procedural aspect of a hospital, and that will suffer from the domain gap problem. The second part of the pipeline is we characterize all of the hospital's nuances into this one compartmentalized config file that informs our data cleaning and pre-processing pipeline. And what you get out of this is a normalized data set. And this is a huge win for scalability because this represents a convergence point between all our hospitals. And any subsequent hospital will still go through the same two-part pipeline to create this normalized data set. So now that we have a convergence point, everything downstream is shareable. We can share code in notably 3 main places. There's feature engineering, label extraction, model training, and validation. Let's start with feature extraction. So how do we extract features? We take the whole encounter, and at every time t, spaced in regular intervals, we take all the data between time 0 and time t at each point in time. And we run that through our featureization process, this gi of x, to create, and we have a whole bunch of featureization methods, and we aggregate all of that into one feature vector to represent that point in time for that specific patient. And we call this vector an instance. What does it really look like? So for each observation type, we have a whole bunch of different features. You have simple statistics like the max and min of a certain vital, say the max body temperature. You can have a mix of numerical and temporal features, like what is the median blood pressure in the past 24 hours. You have purely temporal features, like how much time has passed since the previous measurement, as well as features that go across different observation types. Like, for example, systolic minus diastolic pressure, which has healthcare significance as well, and many more. This is just a select few to give you an idea. And the next part is ground truth extraction. So we don't have the luxury for a clean data set that's labeled by clinicians. They just don't have the time to do that. They don't go through the patient record and tell us, okay, I wish I was alerted at this point in time. That would be nice, but we don't have that. So what we need to do is we need to come up with proxies from the data that we have that represent deterioration. And for us, we decided on 3 proxies: a patient's transfer to ICU, a transfer to palliative care, and if the patient dies. These are all events that represent a patient's deterioration. And if we take this instance of time in blue, we have a buffer window as well as a target window. And if a ground truth event exists within the target window, we consider that a positive instance. And we characterize that by labeling it with a positive weight. So instead of simply scoring 0 and 1 labels, we have a scoring function that takes as argument the feature as well as the ground truth. We want to know what the situation is holistically to weigh the importance of that instance. And the reason we have a buffer window is because we want to avoid data leaks. What this means is we don't want to predict too close to the actual event, because at most times people already know, like clinicians already know, and the data is not inputted perfectly into the EHR every time. So it's possible that the event is already happening, and if you're too close, the model can cheat. It looks at data that is already available, even though it thinks that the ground truth event is not there yet. So we try to avoid that, and we have the model not cheat by adding this buffer window. But of course, like empirically, a 1-0 label works well as well. So with this, the background of your painting is done. All that's left to do is tie the painting together with a foreground object, and that's the model. You have your features, you have your labels. What model do we want to use? What architecture should we pick? Do you want a multi-layer perceptron? You want to throw in a transformer encoder somewhere in there? You want to go with random forest, ADA boost? The truth is it doesn't really matter. We can support all of them. But because we're working with tabular data mostly, and we want to scale quickly, we want to have nice features of explainability and handling of missing data, let's just go with a gradient boosted machine for today. Then what we do to train the model is we perform a typical k-fold cross-validation. But the healthcare piece of this is that we take each encounter and we randomly split them into different buckets. And we pick a period of training time that's typically longer than a year, because you want to see all the seasonality effects within your training set, right? So you take a period of time and you split that into k different buckets. And you do your k-fold validation, where you train on k-1 buckets, you validate on the kth bucket. And you set up a testing period, which is forward in time from your training set, because you want to make sure that it's able to generalize into the future. And then there's threshold selection. Based on our conversations with our clinical partners, we gather requirements of what type of performance do you need for this to be useful. We found that doctors can tolerate 2 false positives for every 1 true positive. And that's to be on the safe side. So what we're aiming for is a greater than 33% precision, and we want to maximize for our recall. And of course, for the model to be useful, it should be at least 50% recall. So we tune our model, and we see that with a greater than 33% recall, we can achieve an 80% sensitivity. So we're in the ballpark, we're in the game, we're good to go. With that, your painting is done. I'll take questions at the end. So now our painting is done. What's next, right? There's still a lot more to do. We want to deploy our work. What this means is you're finished training the model, you want to put it out in the public. You want people to see it. You want to hang it in a museum. For us, that means to deploy the model as a usable service inside the hospital. And what does that entail? We have an amazing platform team at Signal One, and they've done some amazing things for healthcare infrastructure. And today I wanted to show you a subsection of our microservice-based architecture. We'll go through this in detail later, but basically, at one end of the pipeline, we connect to the hospital EHR system. It goes through our machine learning pipeline, and ultimately, we write back our predictions into the EHR as well. Let's zoom into the model service, because that's what we're following for today. What we found is that to make your model useful, you need 3 conceptual endpoints, or real endpoints. You could implement it this way. One is metadata. You want to tell your downstream client about the model, right? What does the model do? What features was the model trained on? What classes does it predict? So that's just the metadata of the model. The inference endpoint is a little bit more interesting. When the inference endpoint is queried, what we do is we pull in data of active patients who are currently in the hospital from our FHIR database that we call the FHIR engine. And we perform prediction, and we pass it downstream to a business logic engine that decides whether or not to alert on that patient based on a set threshold. The ground truth endpoint is another very, very important piece. What it does is it takes in data of recently discharged patients, so people who have already finished their journey in the hospital. And the reason we want to do this is we want to go back and see, were our predictions correct during our inference? So we take in the FHIR data of completed patients. We also take in data of our previous predictions from our own application database. And we go through each prediction, and we do a post-evaluation on where we correct here, where we correct here, where we correct here. And we pass those metrics down to the business logic engine as well. So how do we communicate all this data in our microservice architecture? We have designed this protobuf-based data structure that is a nested encounter-based structure that houses all of this data of what features were extracted, what scores were predicted, as well as attach the ground truth to those predictions. And what we found was that this is a scalable way of presenting the data, because it actually transfers over to different types of ML models that we train. So not just this deterioration prediction model. So with this same way, we get yet another convergence point where everything downstream of the model service is able to be unchanged. big win for scalability. Once you're done, the model service then gets deployed to our Azure environment using Kubernetes and Helm. So let's quickly see this in action. First part, we read in from the hospital EHR system into our own Fire engine. This does a few things. It ingests data in diffs. It aggregates the data, and it anonymizes the data so that we don't need to know the actual patient IDs. And it protects the hospital from our own traffic. So we can load balance that easily. The next thing is we trigger inference on the active patients, and we send the predictions down to the business logic engine that applies alerting and silencing rules. So alerting rules is what I mentioned before. If the risk score is above a certain threshold, we alert. However, we also want to set up silencing rules in order to mitigate alert fatigue to the clinicians. And for example, we have rules such as if a patient recently moved from the ICU, we wouldn't want to alert on that patient for the first 24 hours because we already know that that patient is at risk. If a patient was already alerted, we don't alert the same patient for the next 48 hours because, again, clinicians already know about their situation. We then pass our prediction output down into their hospital EHR system, and we populate our own database with the predictions that we came up with. Then comes the ground truth extraction portion where we pull in data from Fire Engine and the model app database to evaluate our predictions of whether they're right or wrong, and ultimately visualize those metrics in a monitor, in the Signal One monitor, which I'll show you later as well. Awesome, so we're now in the museum, we're deployed, you're all artists, really great. What is the last thing we have to do? Now that your painting is in the museum, you want to monitor your exhibit, right? You want to monitor it for peeling paint. You want to monitor if your performance is your model performance is deteriorating. You want to collect feedback from your guests. Did you like the exhibit? Why not? So let's do the same thing for our model. So what do we monitor for? One thing is we monitor for model performance because our data set is unbalanced, where at the instance level we have probably like a 3% positive case and a 10% positive case at the encounter level. So we monitor for precision and recall. The other thing is the timeliness of the alert. You can't just be correct. You have to be correct at the right time. If you're predicting too late and there's only like an hour before the ground truth event occurs, it's not actionable. At the same time, if you predict a week in advance that a patient is going to deteriorate, it's also not actionable because the signs are not there. There's no confidence in that prediction. So we have to alert in the actionable window of, say, 24 to 72 hours prior to the event. The other thing is we monitor for the volume of alerts. We want to know whether our tool is acting in a stable way. And we also monitor for score distribution shifts. If we suddenly see that on average our risk scores are just tending upwards, then there's something wrong, either a change in the data distribution or a bug somewhere. For example, if a pandemic happens, you'll see your scores rise. But this means that it's now outside of the operating limits of the model, and we may need to retrain it. We also care a lot, not just about the bird's eye view of how the model is doing across the hospital, but also at the level of each patient. You want to see each individual journey and see how their scores trend throughout their journey. So here you see an example of when a patient's score just jumped all of a sudden, right? The next question is why? Why did that score jump? So we also monitor for explainability pieces. So we use SHAP values in a time series manner to figure out why the scores behave the way they do. How do you attribute that score to all the different features that the model was trained on? And here you see that jump coincided with a jump in potassium levels. It coincided with a jump in respiratory rate, blood pressure. So this context allows clinicians to pick the right move, the right next move, right? The other thing we want to monitor for is bias and fairness. We want to have statistical parity on protected factors like the basis of sex. We want to make sure that it is as likely for a male to be scored higher than a female as a female to be scored higher than a male patient. And we do this via the Mann-Whitney U test. We also monitor for data drift at 2 different levels. The first level is at the raw input, the raw data level. Is the data that's coming into our system shifting? That's something we want to know. The other thing we would want to know is whether the features that were extracted by our pipeline shifting. And this is just to make sure that, again, the model is operating within its intended limits. It's close to the validation set, and we do this using the Jensen-Shannon divergence. You can also download periodic reports as PDFs, so you can continuously monitor these statistics in an ongoing manner. Awesome. So that's it. Your painting is in the museum. People are enjoying it. It's fully deployed. Let's do a quick review. First, you framed your problem. And we framed it as a logistic regression problem to send alerts for deteriorating patients. Next, you decided on your palette. You looked through the FHIR data set. You figured out clinically grounded data that's useful for your use case. And you trained your model based on that by putting paint to canvas. And you did a k-fold cross-validation to make sure that you're training things properly, you're tuning your hyperparameters properly, and you talk to your clinical partners to figure out what requirements they have in terms of performance. And then you put your painting in a museum by deploying it, by wrapping your model into a microservice that communicates with a larger platform that ultimately communicates with the hospitals themselves. And we went through how that platform works in general. Then you monitored your exhibit by putting in an ongoing interactive monitor that monitors for performance, it monitors for the behavior of the model in terms of score distribution, in terms of volume of alerts. You did that at a bird's eye view level. You also did that at an individual patient level for you to figure out the different trends. You also monitored for bias and fairness with the Mann-Whitney U test, as well as data drift using Jensen-Shannon divergence. And you can download all of this as a report as well. So thank you so much for coming with me on this journey. I hope that this presentation helped paint a picture of how ML solutions are developed and deployed in real hospitals for a real use case that could potentially save real-life patients. There's still some hard problems we're working on, and I think I don't have much more time to talk about these, but I'll quickly talk about one. One problem that we're facing is evaluating post-deployment, how well are we doing? And I'll tell you why, because once you deploy the model, you inherently shift the underlying distribution, right? Because you now have intervention in the hospital. What if a patient was deteriorating, our model predicted it, it prompted a clinician to act on that patient, and the patient became well again, and they did not deteriorate. Is that a false positive? It shouldn't be. But the question is, how do you collect this feedback without adding cognitive load to the clinician? Because they already have a million things to do. So that's one hard problem that we're working on. And there's many more.
Jullian, sorry to interrupt you,
Yeah.
but we're running a little bit over.
Sure.
So if you want to just quickly wrap it up.
Yeah, I mean, just a quick thank you to the Signal One team. And if you guys would like to chat more about healthcare, ML and healthcare, or if you'd like to join us on our mission, please email careers@signalone.ai.
All right. Thank you, Jullian. Can I have a big round of applause for his presentation today?